So today, we are going to talk about the very last part of our impulse momentum unit. And then next week, we'll spend a couple days reviewing MCQs and FRQs. And we're going to talk today about two-dimensional collisions and two-dimensional recoils. And I'll point out, we won't in this class, but you can extend what we talk about today to three-dimensional collisions and three-dimensional recoils. I like pointing out because a lot of you guys play video games. When I grew up, they're side scrollers only, right? It's like Super Mario Brothers, that kind of thing. That's two dimensions. Going from 2 dimensions to 3 dimensions mathematically is very easy. It's very easy. You just add another dimension, the z-axis, right? The reason it took so long to go from Super Mario Brothers to whatever today, Red Dead Redemption, is because it's just rendering power of computers to actually render the three-dimensional objects, right? But the physics of it is very simple. The physics of three-dimensional stuff is the same as the physics of two-dimensional stuff. You just got to add another axis and therefore another component for every velocity or momentum that you're dealing with. It's hard to visualize for sure, but mathematically it's literally just adding another dimension. And if instead of doing the x and y components of velocities and momenta, you do the x, y, and z components, right? So we won't do that in this class, but that is in your future. Any future physicers or engineers. You'll have to do multivariable calculus in college, which is the calculus of multiple variables. And a lot of what you study in that class is three-dimensional space, because the multivariables, it could be 2, but it also could be 3. It could be 4. It could be 5. It could be 10. Anyone ever heard of string theory? Superstring theory, sometimes it's called. There's several different versions of it, but the most popular version, the one that more people work on, predicts, if it's true, then there are actually 10 spatial dimensions in our universe. What that looks like, our brains can't comprehend it. Whether it's real or not, we don't know, because it hasn't yet made any predictions that we can actually test. So there's no way of confirming it. But it does mathematically work, and it describes the universe as we see it. We just can't test to see if it's actually correct or not. But that might come in your lifetimes. Who knows? Possibly. That's much higher level, though, than what we're going to do. We need to study two-dimensional collisions. So I got 2 objects. I got a blue puck and a gold puck. You can think of a lot of the problems that deal with this kind of stuff are like pool balls, playing pool, where you ignore the rotation. So ignoring the rotation, it's easier to at least conceptualize problems with like air hockey pucks, playing air hockey, where the jets of air that come out of the table greatly reduce the coefficient of friction. So there's not much friction that you have to worry about. So you can think of this like an air hockey table and 2 air hockey pucks going towards each other. One's moving straight down, one's moving up and to the right. And just like in one-dimensional collisions, which are the only ones we've talked about so far, in a two-dimensional collision, momentum will still be conserved. And we can see that by... Actually, before I get there, I forgot to point this out. If I know this is as far as I can zoom in. I tried. If I zoom in more, then it starts zooming out, and then if I zoom out, it goes back in, and then it starts coming out again. So this is as far as I can zoom in. Yeah. So anyway, hopefully you can see what's going on. If not, take my word for it, or check out the video, because the video has a very nice view of it. So when I hit play here, the 2 balls collide and then bounce off, right, which is what we expect. Let me reset that, slow it down a little more. And let's look at the velocity vectors. Each individual puck obviously changes its velocity. Experiences a change in velocity, experiences a change in momentum. But the overall momentum of the system must be the same. It must be the same. And it's hard to see that because you have 2 objects with very different final velocities as compared to their initial velocities. Now, what I'm going to talk about now is not specifically in the AP Physics 1 curriculum. However, I believe that it's a good idea to at least have in your head to understand what's going on. When I have these 2 objects in this location, they have an average center of mass. Have you ever heard center of mass? It's literally just the average location of all the mass within a system. Okay? Oh my gosh. Are you kidding me? It's not me. Oh, Kurt, what did you do? All right, back to what I was saying. So the center, the center of mass is the average location for a system of objects' mass. If you're talking our solar system, the center of mass of the solar system is usually not exactly within the sun. Very often it is, but sometimes it's actually outside the sun, depending on where Jupiter and Saturn are in their orbits. The center of mass of the Earth-Moon system, it's actually within the Earth, but it's almost out towards the edge of the Earth, because the Earth does have so much more mass, but the center of mass isn't at the center of the Earth. It's the average location of the mass of the Earth and the Moon combined. And that center of mass moves with the system. And so as these two objects come together, their average location of mass is going to start approaching the contact point, right? But if you notice, and so the center of mass trail, it's going to be a blue line. After the collision, watch what happens to that center of mass trail. So that blue line right there represents the average location of the mass. It's closer at all times to the blue object because the blue object is 5 kilograms. The gold object is 3 kilograms. So that center of mass must be closer. And then after the collision, it's going in the same direction, same speed. So this isn't a big part of AP Physics 1, but if you can understand it, it makes the conservation of momentum as applied to two-dimensional collisions, in my opinion, a little easier to understand. And then in AP Physics C, which I'm assuming all of you, sans the seniors, will take next year, that's something that we deal with quite a bit, the center of mass of a system, when we do our mechanics portion of that class. And again, as time goes on, it keeps moving in a straight line at constant speed. So that is one way of looking at the conservation of momentum of a system. The system's center of mass momentum does not change, which means since the mass of the whole system doesn't change, then the velocity associated with that center of mass never changes. It never changes direction, even though the particles involved might change direction greatly. Right? And if I make one of the objects a lot heavier, one of the objects a lot smaller, right now the blue mass is 10 times the mass of the gold one. Now the center of mass is going to be a lot closer to the blue mass. It's like right there, right? Almost exactly, but not exactly. Right. Now if I look at the collision, before and after here, and for those that can see it, you see this 4i plus 3j. That's what's called a unit vector notation. You'll learn about that again in Physics C or calculus-based physics and calculus in college. So the velocity of the blue guy before, that's just the components. 4 times I hat is pronounced is the x component. The j signifies the y component. So you don't need to worry about that. But the point is that the before velocity is very different from the after velocity. But if I look at the total momentum before the collision is the same number as the total momentum after the collision. The x component of the total momentum before the collision is 40 kilograms meters per second. The total x direction, x component of the momentum after the collision is 40 kilogram meters per second. Same thing with the y direction. The total y direction, so the total momentum in the y direction before the collision is 26 kilogram meters per second, and after it's 26. If you wanted to know the actual momentum, you just have to take those two vectors, the x component and the y component, and add them to get the actual momentum vector. And notice that this collision, it says total kinetic energy. Total kinetic energy is 133 joules before the collision, 133 joules after the collision. That tells us that the energy is conserved, the kinetic energy is conserved, and therefore this is what type of a collision?
Elastic.
An elastic collision. Okay. Make sense? All right. So again, the center of mass velocity, and if I start changing stuff around, I change the location of the center of mass. Now the gold one is half as big as the blue one, so the center of mass should start a lot closer to the gold one than it did the blue one. And because momentum is conserved in this collision, that center of mass momentum stays constant. Okay. All right. Are we still recording here? Yes. All right. So now go ahead and take out that paper that you picked up on the way in. We're going to work a couple example problems. One with a collision in 2 dimensions, and then one with an explosion/recoil in 2 dimensions. So the first one, let me copy down the table real quick. 1 kilogram. Sorry, Kurt was supposed to do this before class 2, but he wasn't here to do it. So. 1 x direction momentum. I'm going to call that px and p naught comma x, the initial momentum in the x direction. I'll do it like it says on the table. Kilograms times meters per second. And then the momentum in the y direction. And kilograms times meters per second. And then for mass 2, note if you look at the diagram there, it looks very similar to what we were just talking about. Momentum in the x direction in kilograms times meters per second. Momentum in the y direction. And then we're going to talk about what went on before and what went on after the collision. Okay. All right, so 2 objects of masses 1 and 4 kilograms respectively are free to slide on a horizontal frictionless surface. The objects collide and the magnitude and directions of the velocities of the 2 objects before and after the collision are shown on the diagram above. And then it says parentheses and it tells you various values for the sine, cosine, and tangent of 37 degrees. I've pointed this out before, but just so you know, on your AP Physics 1 formula sheet, there's a table that says values of trigonometric functions for common angles. Those are your special triangles, your 30, 60, 90, and your 45, 45, 90, and then 0 and 90 degree angles, which pop up a lot, and then the 37 degree angle, which corresponds to a 3, 4, 5 right triangle. The reason they put that there is not because most triangles that you encounter, most momentum, or most vector decomposition that you will end up encountering in real everyday life, as far as like engineering and physics goes, are going to be those angles. It's just if you can deal with the trigonometry of those angles, it's just a matter of putting in a calculator what the sine of the angle is. So this just takes some of the tedium related to the math out of the picture. And then just so you know, yeah, so here it says sine 37 is 0.6, cosine of 37 is 0.8, tangent of 37 is 0.75. The reason that they put those there on that particular question is because before a few years ago, I think this was an AP, does it say? No, this is an AP Physics B question from long before you were born, from 1984. And when that question came out, calculators weren't allowed on the multiple choice section of the AP Physics exams, any of them. And so that's why they gave you those, because they can't give you an angle and expect you to know the sine, cosine, or tangent. And again, in physics, you're not really being assessed on your math skill. Yes, you are to an extent, but that's why I always say the physics is done at this point. Now it's just a matter of entering stuff in your calculator. So to answer the questions with these kinds of problems, you gotta know the physics, and obviously you gotta be able to do the math. But it's assumed as juniors in AP Physics that your math skill is at least pretty good, to where so good that we're not really assessing how well you know the math, because you should already know that. It's how well you know the physics. Okay. So all that being said, part A says calculate the x and y components, px and py, of the momenta of the 2 objects before and after the collision, and write your results in the proper places in the following table. So let's look at M1 first. Before the collision, what is the momentum in the x direction? Let's calculate it. So this will be px naught. I'll put it like that. You can put it however you want, but I want to say the initial momentum in the x direction for mass 1. Right? If you want to use a comma, you can. If not, whatever. You can put it in a table form, do whatever makes sense to you. I like indicating everything on the actual thing. So I have px naught 1. Notice I don't have to put the vector symbol over the top because I'm indicating the direction with the subscript x. So the initial momentum in the x direction. Do I have to do, yeah, It's 16, right? The mass is it's m1 times vx naught 1, but the mass is 16 kilogram meters per second. No, the mass is 1. The velocity is 16 meters per second, so that's going to be 16 kilograms times meters per second. So that's the initial momentum in the x direction for mass 1. So I'm going to put that, 16. And I only have to put the number. We know this because the units are at the top of the column in the table. What's the initial momentum before the collision for M1 in the y direction? 0. It's not moving in the y direction. So we can just put 0 there. Now for the hard part. What are the momenta in the x and y direction for M2 before the collision? It's not hard, I was just kidding. 0. It's not moving, right? M2 is not moving before the collision. So the initial momentum in the x and y direction for M2 is 0. It's not moving. So let's talk about the physics here a little bit. Before the collision, all of the momentum is in the x direction, right? The center of mass of the system, center of mass momentum of the system is to the right. It's moving to the right. And before the collision, it is entirely located within M1. Not the center of mass, but the momentum. All of the momentum is in M1 as it moves towards M2. All right, well, let's talk about after the collision. How many zeros do I have in here after the collision?
1.
I have 1 0. And which one's that?
The first one.
Yep. The final the momentum of M1 in the x direction after the collision is 0, because at that point, the object is moving straight down, so its momentum in the x direction is 0. It does now have momentum in the y direction, though. So I'm going to say the final momentum in the y direction for object 1 is going to be m1 times the final velocity in the y direction for object 1. Right, just p equals mv. You got a question? You're just stretching.
No, I have a question.
Yep.
So, like, if the ball is moving down instead of up, would the y be negative?
Yes.
Okay.
Yes. Yeah, for sure. That's a good point. I actually messed that up last period because I forgot to put the negative. Yeah, the object is moving down. Look at our we got the coordinate system right there. Up's positive y, to the right positive x. Velocity and momentum, most definitely vectors. So because m1 is moving down, its velocity is negative 12.
So then would that also work if before the collision, M1 was moving to the left instead of the right?
Yeah.
Okay.
It would be negative, yeah. So m1 is going to be 1 times that final velocity, which is in the y direction, which is negative 12. So I have negative 12 kilogram times meters per second for the final velocity, final momentum for m1 after the collision. That's going to be negative 12. All right. Now m2 after the collision, we got to be a little more specific about. We got to be a little more careful because we know that m2 has a velocity that is up and to the right. So that's v2. v2 final. And we have our coordinate system right there on my paper. Y is up, x is to the right. This guy doesn't align with those axes, so what do we need to do with it? We need to decompose it into the x component and the y component. And we are given this angle right here. And hopefully we've done this enough times so that it's second nature. The horizontal component is the actual velocity times the cosine of the angle. The adjacent component, I should say. The opposite component is the actual vector, v2, times the sine of the angle. And so those are what I got to decompose the v in order to have the x and y components for the p, for the momentum. And so the final momentum in the x direction for object 2 is going to be m2 times the final velocity. I'll write this out explicitly as I would if I was doing this problem. Final velocity in the x direction for object 2 which is going to be m2, because I know the final velocity in the x direction for object 2 is going to be v2 cosine theta. So that's m2 times v2 cosine theta. And that's going to be m2 is 4, v2 is 5, right? 5 meters per second, times the cosine of 37. And again, if you didn't have that table of values and you didn't have a calculator, good luck doing that unless you have memorized what the cosine of 37 is. But we can just look on the paper and say, well, the cosine of 37 is approximately 0.8. So 4 times 5 is 20. Cosine of 37 is approximately 0.8. 20 times 0.8 is 16 kilogram meters per second. Doesn't that make sense? 16. Before the collision, the momentum in the x direction was 16 kilogram meters per second. After the collision, there's no more momentum in the x direction from m1. But momentum in the x direction must be conserved. So the momentum in the x direction has been transferred to m2. And so it carries the x direction momentum now. Again, total momentum in the x direction has to equal the total momentum in the y direction. Which tells us that we probably should know what goes in this box. Can anyone tell me what should go in this box? 12. Well, let's prove it, just to be sure. Yeah, I have 0 momentum in the y direction before the collision, so I must have 0 momentum in the y direction after the collision. So those two numbers need to add to 0. But let's calculate it anyway in the same way we did this one. Final momentum in the y direction for object 2 equals mass 2 times final velocity in the y direction for object 2, which is m2 times in the final direction in the final velocity in the y direction is v2 sine theta. So m2 times v2 sine theta, which is 4 times 5 times the sine of 37, which is 20. Sine of 37.6, right? Sine of 37 is approximately equal to 0.6. So that is sure enough 12 kilograms times meters per second. Make sense? Remember, momentum's a vector, so if you got two-dimensional collisions, momentum must be conserved overall. It must be conserved in the x direction and in the y direction. And then B, I'm not going to take too long because we ran out of time last period. B says show, using the data that you listed in the table, that the linear momentum is conserved in this collision. Well, here you could just say Px naught for the system equals Px final for the system. Py naught for the system equals Py final for the system. You could just say the table shows us that the total momentum before and after the collision in the x direction is 0. The total momentum in the x direction is the same before and after the collision, and the total momentum in the y direction is the same before and after the collision. So it's that simple. That's pretty simple one. The one I want to focus on, C and D. The reason I want to focus on C and D is because this kind of illustrates the difference between how they approached AP exams back in the day, in 1984, when you were not born, and I was actually alive because I'm that old. I was in kindergarten, but I was that old. I am that old. But back in the day, they would ask you questions like this. Part C says, calculate the kinetic energy of the two object system before and after the collision. And part D says, is kinetic energy conserved in the collision? If you had a question like this on the AP Physics 1 exam, C and D would probably be a single part. And it would say this. It would say, was this collision elastic? Justify your answer. Okay. Note that C and D here are asking that same thing, but they're not assessing whether you know the vocabulary, the whole elastic collision aspect of the vocabulary. But it's asking you to do the same thing, because in order to determine whether a collision is elastic or not, or inelastic or partially, totally inelastic, you have to know, is kinetic energy conserved or not. Right? So this is kind of walking you through it, whereas on the AP Physics 1 exam, it would be more like, is it elastic? Tell us why. And so if you had this question on a test in this class or on the AP exam, it would say, it would be likely to say, is the collision elastic? And then your brain needs to say, all right, well, that means I need to check to see if kinetic energy is conserved. And if it is conserved, the collision was elastic. If it's not conserved, we could say here it's definitely not going to be totally inelastic because the objects don't stick together, but it could be partially inelastic, or it will necessarily be partially inelastic if kinetic energy isn't conserved. So for part C, in this particular one, I just need to note the initial kinetic energy and the final kinetic energy. The initial kinetic energy is 1/2 m1 times v naught 1 squared plus 1/2 m2 times v naught 2 squared. That's my initial kinetic energy in the system. Simplify our lives by noting that the initial velocity of m2 is 0, so this whole term goes away. So my initial kinetic energy is purely the kinetic energy of m1, and so that's going to be 1/2 times m1, which is 1, times v naught 1, can't believe I forgot, 16 squared. What's 16 squared? Someone knew it last period, I already forgot. 16 squared? 256. And 1/2 of that is 128. So 128, what are the units for kinetic energy? Joules. Who said don't know? Dude, you're behind. You need to know that. Okay, and my final kinetic energy is going to be 1/2 m1 v1 squared, final velocity for 1 squared, plus 1/2 m2 v2 squared. That both of the objects have kinetic energy. Remember, kinetic energy is not a vector. So we don't need to worry about direction. We don't need to worry about vector decomposition. All we care about is the overall speed. So it's going to be 1/2 m1, which is 1, times v final for 1, which was 12 squared, plus 1/2 m2, which was 4, times v final for object 2, which is 5 squared. 144, 1/2, 72, right? Plus 5 squares, 25 times 4 is 100, 1/2 of that is 50. So that is 122 joules.
Could you not just do 244 and then divide by 2?
Yeah.
Yeah, factor that 1/2.
Yeah. Okay, so is kinetic energy conserved here? Nope. Now what you can conclude is that that collision was very bouncy, just wasn't 100% bouncy. Why was it very bouncy? Because not much kinetic energy was lost at all. Okay. Now, I'm going to point this out because this is a question I had, and I remember the conversation I had with my community college physics professor when finally understanding why. Where does that energy go? It's real easy to understand that generates some sound waves, right? When I talk, like some of the food that I ate and the energy that I derived from it, some of it is being used to vibrate my vocal cords. As my vocal cords vibrate, and you'll learn this when you learn about sound waves. We used to do sound waves in AP Physics 1, but not anymore. They vibrate the air molecules that surround my vocal cords, which produce sound waves. It requires energy. So anytime you have a collision that generates sound, some of the kinetic energy of the objects before gets converted to sound waves. This collision here could have happened in space, though. In space, there's no sound. Have you ever seen the original Alien movie? Has anyone ever seen the original Alien? One of the taglines on the posters, in space, no one can hear you scream. Because in space, there's no sound. So when you watch like Star Wars and whatever other science fiction movies where they have explosions in space and it's all, you have to have the sound because it would be weird if there was no sound. But in reality, there would be no sound if you saw an explosion in space. But you would still lose energy. You'd still lose some energy. And that's because of thermodynamics. That's because of heat and temperature. If I punch my hand, right, this hand is now and not because of the biology, not because of like the inflammation process and all that, but when I punch the wall, that wall is slightly higher temperature than it was before I punched it. Some of the kinetic energy of my hand got converted into the sound that you hear. It also increased the temperature of the wall just a little bit. That is unavoidable. You cannot escape that. That's why your cars need radiators in them, because you must radiate the heat out. That is unavoidable. You cannot have a car engine that doesn't produce a certain amount of heat. And that's because anytime you have material in contact that either collides or rubs like friction, anytime that happens, the atoms involved with the surfaces jiggle a little bit faster than they did before, which means their temperature goes up, which means you have internal energy, or internal thermal energy, as sometimes it's called. You have an increase in that internal thermal energy of that system just by virtue of the fact that the objects come into contact. Okay, so that's why collisions, even if they produce no sound, they will always produce at least a little tiny bit of heat. Unless we're talking like ideal gas molecule collisions, because those produce so little heat that it's like pretty much negligible. But understand that that's where it goes. And that is unavoidable. It's unavoidable. You cannot have a car engine that doesn't produce heat to get your car to go. It just cannot happen, because as the pistons move up and down within the cylinders, there's going to be friction. They're going to get the atoms in the engine block, the iron atoms in the engine block, to vibrate faster than they were before you turned your car on, and you will inevitably build up some heat. For the same reason, when you slap the board, it's going to increase the temperature. Maybe not by an amount that I can feel, but if I was in a high-tech lab that had a very high-tech temperature sensor, I could definitely measure that. In fact, there's a funny, brought this up last period, there's a funny physics problem that says, how many times do you have to slap a raw chicken to cook it, right? You might have heard that before. Now, in reality, it's never going to work, because if you start slapping the chicken, eventually it'll be hotter than your hand, and when you make contact, heat will then transfer back to your hand instead of going into the chicken. But every time you slap the chicken, theoretically, if you get in outer space where it won't radiate heat into the environment, every time you slap the chicken, its atoms are going to vibrate just a little bit more than they did before. And so eventually it will heat up, theoretically. Eventually it'll heat up to where it will be cooked, right? I recommend not trying it. If you try it on the Earth's surface, it's definitely not going to work, because there's going to be a point relatively soon after you start the experiment where the chicken will just radiate the heat out into the environment faster than you can add to it by slapping it. But it is a funny physics problem, an actual physics problem where people would have to do the calculation. Some physics problem writers are silly like that. But anyway. So again, take home point, C and D in this problem, if you saw a question like this in AP Physics 1, it more than likely would have said something like, is the collision elastic? And then justify your answer. And you could say, no, the collision is not elastic because kinetic energy was not conserved. And I proved that by calculating whether kinetic energy was conserved or not. Make sense? All right. So let's talk about, what am I doing? Let's talk about another two-dimensional momentum problem. This is the last example from the notes. So if you got the notes that I gave you, pull them out. If not, just follow along. This will be a two-dimensional recoil event. And there isn't a diagram for it, so let me just draw a diagram real quick.
Example number 7.
Example number 7, yes. This marker is just about done. All right. So I'm going to read it all real quick and then list everything out so we can solve the problem. So an unstable nucleus of mass 17 times 10 to the negative 27th kilograms, initially at rest, disintegrates into 3 particles. One of the particles has a mass of 5 times 10 to the negative 27th kilograms and moves along the positive y-axis with a speed of 6 times 10 to the 6 meters per second, 6 million meters per second. Another particle has a mass of 1 times 10 to the negative 26 kilograms and moves along the positive x-axis with a speed of 4 times 10 to the 6 meters per second. determine the magnitude and direction of the third particle's velocity. Notice that for now you may assume that mass is also conserved in the disintegration process. In an actual nuclear decay, is mass conserved? Does anyone know? It's not. What happens to that mass? Gets turned into electromagnetic radiation, i.e. light. Right? By an equation you might have heard of. You ever heard of this equation? You ever seen it? You know where I'm going with this?
Never seen that one before.
Never seen that before? You've never seen the real one, probably. So that's just a simplification. That's if the object is not moving before. And in this problem, the object is at rest. This is how much, and so after this guy explodes, he's going to be 3 particles. And the mass of those 3 particles added together will necessarily be less than the amount of mass that it had as a whole. And that mass just doesn't disappear, and it doesn't technically convert. A lot of people say it converts into energy. There's a more complicated process that Einstein described, and it's kind of over my head. But it essentially becomes energy. It becomes energy. That's why nuclear bombs, that's what nuclear reactions do in nuclear power plants or nuclear bombs. They take mass and they convert it to energy in the form of in a bomb, an explosion, in the form of or in the form of nuclear power plants. They just convert it to heat, which they then use to produce power, just like coal power plants and geothermal power plants and all that stuff. So I like pointing this out though because this everyone knows. But if this object is moving before it disintegrates, this isn't true. If the object is moving, then this is the real equation. P, which is momentum, right? That's the real equation. You need to know that for this class? No, of course not. But since it does involve momentum, it's a good time to talk about it. So if the particle has momentum before the disintegration process, then it's actually going to produce quite a bit more energy. But if the momentum is 0, then that whole term goes away. Then I can square root both sides, and I get what everyone knows, E equals mc squared. And just say, a lot of students when they're learning physics are like, how did you just say, was Einstein just sitting around one day and he's like, I bet E equals mc squared. Like, no, there's a lot of stuff, a lot of crazy theoretical physics that's way over my head went into deriving that. I've looked at that before too, and it's really hard to follow. You got to know like tensor calculus and vector calculus and all that good stuff. But anyway, so we have a before picture and we have an after picture. In the after picture, I have a particle that's moving along the positive y-axis. I'm going to call this guy, make it a little bigger. Call this guy M1. He's moving along the positive y-axis. So that's final velocity for object 1. I have another particle that has a certain mass, moves along the positive x-axis. So it's going to be M2, moving along the positive x-axis. So I'll call that final velocity for object 2. And just with what you know about conservation of momentum in general, and what we kind of talked about in the previous problem, there's going to be a third part, the third part of this. What direction is it going to be moving in? In what quadrant will it be moving in? The third quadrant, right? Because I got to have momentum. If the total momentum before the explosion, before the decay is 0, which means I have momentum to the right now. That must be compensated by momentum to the left. And then I have momentum that's up that must be compensated by momentum down. So the third particle must be moving in both the negative x and the negative y directions in order to satisfy the conservation of momentum. So M3 must be moving down and to the left with final velocity V3. Right? We're running short on time. Right. So let me list everything down real quick. Notice I didn't call this guy M1, right? Because I got 3 objects after that are all combined, so it's like the opposite of an inelastic collision. So I'll say M1 is given to me. That is one particle has a mass 5 times 10 to the negative 27th. and it's moving with a speed after, so a speed v1 in the y direction, so vy, comma 1, sorry, v1 comma y, of 6 times 10 to the 6, or 6 million meters per second. That's typical speeds for particles. Another particle of mass 1 times 10 to the negative 26, so that's I'm going to call M2. 1 times 10 to the negative 26 kilograms is moving V2 in the x direction. Oh, the first guy. Oh, I'm getting lost. No, the first guy's in the y direction. The second guy's in the x direction. That's going to be 4 times 10 to the 6 meters per second. Notice we're not given M3. Can I determine M3 from the given information in this problem? Yeah. I'm given the mass of this guy. And I'm told that we can ignore the change in mass that would actually happen in reality. And so I just take this guy's mass, which is 17 times 10 to the negative 27th, and then I subtract M1 and M2. So minus 5 times 10 to the negative 27th, minus 1 times 10 to the negative 26th. And I get 2 times 10 to the negative 27th. Please note, M2 is larger than M1, yes? You want to understand scientific notation well enough to where that's relatively obvious. Okay. And so what we're looking for is the final velocity for object 3 and the direction. Well, the final velocity for object 3, which means I need its x component and I need its y component, right? Just like when we did projectiles, just like when we did forces, not like when we did energy. Yes, sometimes we had to decompose force vectors to do energy, but energy is not a vector. Because we're dealing with vectors here, we momentum, which is a vector, we treat it like we did velocity and like force. So I can split it in the x and y directions. I can say, in the x direction, the net initial momentum, px naught, equals the net final momentum in the x direction, px. What's the initial momentum in the x direction? 0. And then after the nuclear disintegration, I have M2 with a positive momentum, so M2 times V2 in the x direction, which I know both of those, and then plus the momentum of M3, the x component of the momentum of M3. So really what I'm dealing with is not V3 itself, but the x component of V3. I got to decompose this guy, just like I did in the last problem. And so it says determine the direction as well, and I like measuring my directions with respect to the horizontal because that's what you typically do in pre-cal and calculus. So I'm actually going to call this my angle that I'm looking for. And then in my answer I can specify at this many degrees below the negative x-axis, if you want to specify it that way. But when I do that decomposition, I know that the x direction velocity is v3 cosine theta, and the y direction velocity is v3 sine theta. And they both are negative, but I'm going to let the math tell me that they're negative. Right, we always put plus m3 times v3 in the x direction, which is v3 cosine theta. And notice if I knew numbers for everything here, I could subtract this term over here and I calculate a negative velocity for v3. So the math tells me it's negative. So I put in a plus because I'm literally adding the momenta and then letting the math tell me whether it's negative or not. Now what I'm really looking for here, because the question says, determine the magnitude and direction of the third particle's velocity. So I need the magnitude, v3, and I need the direction specified by the angle theta. So that means in that one equation I got two unknowns. Which means just like we did a million times before, I also have to look at the y direction. What's the initial momentum in the y direction? 0. The momentum in the y direction is carried in m1 and m3, so the momentum in the y direction is m1 times the final velocity in the y direction for m1, and that plus the momentum for m3 in the y direction, which just like it was here, it's going to be m3 times v3, but not cosine theta. Now we got the sine component, and again we expect the direction to be negative for that particular component. Now I have two equations and I have two unknowns.
You solve for V3 on either one of them.
Yeah, that's what I would do. I would solve one of them, or you could just set this guy equal to that guy because they're both equal to 0.
That's true.
It's up to you. It's up to you. That is a little trickier though because you do have to do inverse trig to get the angle, but we definitely don't have time to finish that up. Okay. So that's how you would set it up though, a two-dimensional recoil. Yeah.
So would M3 follow like the center of gravity line between M1 and M3?
Say again?
Would M3 follow the center of gravity line between M1 and M3?
The center of mass velocity? The center of mass is going to stay put. As these three guys move away from each other, the center of mass is going to stay right there in the middle. Because the object was not moving before the disintegration. Now, if it was moving first, if this guy was moving to the right, then as they exploded, V1 probably has an X component a little bit, but yeah, the center of mass would still be moving to the right at the same speed it was before the disintegration.